All right, good morning. I'm from Cypress Envirosystems, as John says, and what I'd like to talk about today is how to make dumb buildings smart, essentially. The title is Non-Invasive Retrofit of Existing Buildings, but existing buildings we mean buildings that were built 15 years or more ago, and how do we make them smart? If you look at new buildings today, they have sensors, they have controls, they can feed data into the cloud, you can do analytics, you can look at data on your cell phone. But existing buildings, a lot of the older ones, you really have no visibility. So how do we make those smart? And our approach is to do it non-invasively, meaning with a minimum of labor, minimum of occupant disruption. And what I want to share with you is some technologies that we have developed to do that. So first, what do we mean by dumb buildings? And John mentioned, an obvious one, pneumatic thermostats, the one here on the upper left-hand corner here, right? Those thermostats, when you turn the knob, you hear a hissing sound, right? Because it's only air behind it. There's no wires, there's no communication, there's no backnet, there's no electric power. It's all compressed air, and you have to turn a knob to change the temperature. So that's a technology that's been around for 100 years. It was developed by Johnson Controls in 1896. And then also widespread, a lot of buildings you find steam systems, steam traps, they're mechanical devices. There's no data coming out of them. If they fail, if the steam leaks, nobody knows. If it blocks, nobody knows. You have to do manual audits. Other manual devices are like dial gauges, pressure gauges, flow, temperature, or magnehelix, delta P across a HEPA filter. Well, a lot of people run around with notepads and they copy down a number, type it into Excel, very labor intensive in these older buildings. So how do we make these dumb buildings smart? Now, what we've done is created a suite of non-invasive technologies that in 15 minutes goes and makes the dumb equipment smart, and now you get data, you can get control. And the whole philosophy is to avoid cutting open walls, avoid running wires, or avoid disrupting occupants and so on. Keep everything to like 15-minute retrofit, and then have wireless devices, clamp-on devices, optical devices that would interface with the existing system. So, for example, one of the ones that first product we developed was this gauge reader, where wherever you had a dial gauge, let's say a pressure gauge, instead of walking up, looking at it, and copying down the number, we have this electronic eyeball that fits over it. Just put this hockey puck size device over it, and it reads it optically, turns it into a digital value, and transmits it wirelessly. Now you can see it on your phone, you can trend it, you can get it on your automation system. And that's really what we mean by non-invasive. Just stick it on, in a few minutes you get the data. And then the wireless pneumatic thermostat is also a similar idea. Take off the old thermostat, put in a new one, and in 15 minutes you have digital pneumatics, you have networked pneumatics, and now you can do all those things with demand response, you can do energy savings, all those good things that we are used to in modern buildings. Now for the presentation today, I'm going to focus on the pneumatic thermostat. If we have time, I'd be happy to take questions on the other devices. But I think, as John says, we have so many buildings in New York City with induction units, with pneumatics, that this seems like almost a no-brainer. In fact, it's not only in New York City, it's all around the country. Data from the Department of Energy shows that if you look at non-residential buildings, about 70% of our non-residential buildings have pneumatic zone controls. So just think about that. You get really no control, no data from those zones, and you can't implement things. You can't shut down a zone if nobody's there. You're heating and cooling. You can't respond to demand response signals from the utility. If there's an expensive power day the next day, you can't turn down temperature or do a setback. So it's really a huge problem. Now, we were fortunate, we've actually been doing this for about almost 8 years now, and we've learned a lot from our customers. So what I'm about to share with you is, from folks that we've already installed this in, and, really listen to the chief engineers and think about how we can optimize it, make it non-invasive and so on. So the idea, again, is replacing the existing pneumatic thermostat with a digital device. Now in this case it's wireless and it's battery operated, so you don't need to run any wires. The batteries last about 3 to 5 years, and all it is just removing the old one, connecting the tube, hang it back on the wall. Now you go from the device on the left, which is fully manual, meaning it has a manual set point control. You have to walk up to turn the knob to change it. There's no remote readings, there's no diagnostic, no trending. You cannot connect it to your automation system. Then you go within 15 minutes to install it. You would have this digital device that now you can remotely trend temperature. You can know what set points are there. You can remotely change set points. The unit auto-calibrates. For those of you who know pneumatics, a lot of times you need a lot of manual calibration. These units would auto-calibrate. It'll connect to your building automation system from Siemens, from Honeywell, from Johnson, and all this takes 15 minutes to do, compared to probably days even for conventional technology. Because if you look at conventional technology, if you didn't use this wireless pneumatic thermostat, you're talking about ripping open walls and ceilings. You're not only replacing the thermostat, you're replacing the actuator. There's the damper actuator. You're replacing that with a motor, a direct coupled actuator. You're running power lines. You're running signal lines. And that is just very invasive. Now, if you have older buildings with asbestos, it's even worse. Then you need to do abatement, and you need to move people out of the space. So all those things cause a lot of extra cost and disruption, which is why so many buildings with the old thermostat just stay that way, because it's just too expensive to upgrade them. Now, with the device that we have, basically it takes away all of that and gets you the digital benefits. So now once you install it, it's really easy to install, but once you install it, what kind of benefits do you get? Well, they're very similar to what you would expect from digital control, what we call DDC. You definitely get improved energy efficiency. You'll get better tenant satisfaction, because now you can monitor, trend the place. If it gets too hot or too cold, you'll get an alarm. You can be proactive about keeping people comfortable. There's a reduced maintenance effort, because you can trend and you can troubleshoot more easily. You have a lot of data. And you can do things like demand response. As John was mentioning earlier, if there's peak load days, you can then send signals and they automatically adjust set points to avoid a peak load, which would cost you a lot of demand charges if you didn't respond. So these units will let you remotely and go and do demand management. And for those folks who have buildings you're looking at LEED approval, then the LEED points are really attractive as well. Let me talk a little bit more detail about exactly how you get energy savings and how you get maintenance savings. This is a busy chart, but if you look at the very bottom row here, it could be something as simple as enforcing set point, like no higher than 74 degrees, no lower than like 68 degrees, just keeping people in a band, making sure there's no simultaneous heating and cooling. It could be as simple as that as a first strategy. Then you can also do more advanced things like deadband control, and I'll talk about that, where you have separate heating and cooling set points. You can do things like duct static pressure control, adjusting your fan speeds for duct static pressure. You can do supply air temperature resets. You can do optimal start-stop. I'm not going to talk about all of these, because if for those of you who are familiar with digital controls or new buildings, they're just what all the new buildings do now. It's no different than what we do with new buildings. The only thing is different is that we now allow older pneumatic buildings to do these same strategies. So all the chief engineers, they already are familiar with all of these approaches. It's just how do we get a dumb building now to do these smart strategies. Now, I will share with you one example. I mentioned set points, right? So how do we use set point control to save energy? Now, one way is that we can make sure, like I said, there's enforcing set point limits and avoid simultaneous heating and cooling. Well, one additional strategy that's very popular from the customers that we have worked with is putting in a deadband, like a separate heating and cooling set point. So let's say that if you are over 72 degrees, then it'll start cooling. If you're below 68, it'll start heating. And between those two, it's just ventilation. So you basically have a bit of a deadband, and you can adjust that for nighttime and daytime. Now this is different from conventional, right? If you look on the left chart here, conventional thermostat, you have one set point, If you go above that, it starts cooling. If you go temperature falls below, it starts heating, and it always goes around that set point. Well, if you have a deadband, you can control what you want, where you heat and cool. Now, here's a chart that kind of shows you how that works. This is a time. It goes from this little stair steps here are days. So basically, at night, you can make your band really wide. So let's say it goes from like 65 to 78, and you let your temperature vary. Because at night, you don't really care to heat or cool the space. You can have very broad set points, so your temperature varies back and forth. During the daytime, you're going to narrow it, maybe have 72 degrees or 70 to 72. People are comfortable, and at night you wind it in again. So by doing that, you are really keeping control of the temperature when you need it. The light blue line here is the cooling set point. The red line here is the heating set point, and you'd see here's these 1 day at a time. So at night it broadens the band, at daytime it closes the band. The dark blue line is the zone temperature, so you can see when it's occupied, it's really comfortable, and then when it's unoccupied, it just drifts. It lets it go up and down as the temperature requires, because nobody's there, nobody cares. We're not going to spend a lot of money to heat or cool the space, right? So these are some more intelligent controls that we can do to adjust, the space so that we don't waste energy when the space is unoccupied, but we keep it comfortable when people are there. So that's one example of a strategy how using this digital control can help you. Another way is a little bit more advanced would be to adjust the duct static pressure. Now we talked earlier about the induction units, how much air we're flowing through, how much duct static pressure we're maintaining, but actually we don't always have to maintain the same duct static pressure, right? Most of the systems were designed so that you have enough air to go through to heat and cool the space at the worst load. So if you have your fans, you're blowing the fans enough to have enough air to heat and cool the space. Well, what if the space is kind of comfortable? You don't need that much air flowing through. So what we do with the thermostats, we collect all the data, and then we say, well, how many zones are actually comfortable? And if it's comfortable, we can dial back the frequency of the fans, the variable speed drives, and you can save energy by going back down to maybe minimum air exchange, right, for indoor air quality, rather than the maximum for heating and cooling. So by getting the data from the thermostats, now you can control your fans, you can throttle back your fan data, and by moving less air through, you're also using less heating and cooling for the makeup air coming in. So a lot of different ways that you can save energy by doing the control and the data from the thermostats. Now, what type of savings are we talking about? Usually, around the country, we average around 20 cents to 25 cents per square foot. That would be a metric, roughly the type of savings that we can achieve by putting in this technology. It's very consistent. If you compare a new building with digital controls and an old building, you're usually around, 20–25% difference in terms of energy consumption. That translates to around 20–25 cents per square foot. Now, the cost to put this in, usually around $1, plus or minus 20 cents. So usually the payback actually is usually about 3 years, 4 years. But if you have utility rebates, then it drops to much less, so 1.5 to 2 years. Yes, John. Usually around like 12 cents per kilowatt hour. So. Yeah, so obviously much faster payback, and also it does if you have heating steam. Let's say if Con Ed steam at $40 per 1,000 pounds, that'll pay back really fast, right? I mean, some of the heating is very expensive, so obviously the higher your energy cost, the more faster to pay back. So this data that I'm showing here is collected independently. This is from the California Energy Commission. So we have a lot of independent M&V data through different types of buildings. And in fact, I'll share this with you too. The Department of Energy just did a study. This is a building in Washington, D.C. Did a 2-year study, and then they did a model. This is Oak Ridge National Labs. They did a model for different parts of the country, large buildings, small buildings, and the type of payback that you get. And this is a one that is published on the GSA website. So basically, they said it's a no-brainer. Almost any building, anywhere, will pay back, in like 5 years. Most buildings is more like 2 to 3 years. So it's really, the climate and the cost of the energy. Yeah, the DOE study was really telling.
All right, we have copies of that study.
Oh, yeah, thanks. Now, that's the energy saving side of the benefits. Now, there's also savings on the maintenance and the tenant comfort side as well. So if you look at the tenant comfort, and it actually goes hand in hand with maintenance savings, is that once you have all this data and you're trending it and you can react to it, you know, if space gets too hot or too cold, you get an alarm, right? Rather than have someone call in and complain, and then you have to react very quickly, you have to send someone up to the space. Sometimes it's not even a problem. They just call and then you go up and, you know, there's nothing wrong, or they just, you know, talk with the tenant a little bit. Well, if you have the trending, the alarming, and you have the remote control, now you can actually see what's happening. You can adjust and prevent people from having the complaint in the first place. So this is a study from Cushman and Wakefield. We actually did it for, this is a building, financial district. It's a high rise with, you know, very picky private equity tenants, and they have a lot of complaints in the past. In 2009, just from March till November, he had like 29 hot and cold calls. In fact, this customer was so upset they thought they might move to another building. Then they put in these wireless pneumatic thermostats, and they were able to do this trending and alarming, as I mentioned. They cut down the hot and cold calls by 2/3. So that was a huge difference. The tenants were much happier. They renewed the lease, and we found out that we ended up saving quite a bit of maintenance labor too, because every call that they could avoid was really over 30 minutes of a technician's time, and you could then do things remotely. You could keep people happy and use less labor. So this was a key case study for us from Cushman and Wakefield. And we've now done the same type of study for dozens more building, and the same pattern holds. Really, it's usually around 60 to 80% reduction in hot and cold calls after you have this installed. And then another way that we have maintenance savings and also energy savings is just having the data lets you now analyze it. You can do diagnostics on it. So if you look at the charts here, they look at pressure, temperature, zone temperature, and it's over time. This is like midnight to midnight in one day. Well, for those people who know pneumatic systems, if you look at the charts, the top one looks okay. It looks great. It's a green, you know, everything's working as it should. The next two have various problems. It has whether reset velocity controller is not calibrated or a damper is stuck open. And by looking at the charts and the relationship between the air pressure, the zone temperature, and the set points, you can kind of figure out, well, this zone is not working well, and this zone has probably a stuck damper, this zone is probably not calibrated. Then you can send someone there to correct the problems. So you really have sort of a ongoing commissioning tool, if you will, and you can feed this data into the cloud, and then you'll hear from another speaker later on. You could feed it into you know, cloud analytics that will let you integrate it now with your air handler, with your chiller data, and you have, you know, your complete building. Once you have all this data, a lot of the trends really tell you how to maintain your building at a top level, rather than, you know, if something happens you just don't know and it degrades, right? You waste energy. So the visibility from the data is huge. And that leads into LEED points. You know, LEED version 4, this whole ongoing commissioning, continuous commissioning is a big deal, right? Because what you want to do is constantly monitor for faults and detect them, correct them before they become a waste of energy. So by doing what I just mentioned, you get a lot of LEED points if you were going for LEED certification. So those are a number of the different benefits that we have seen our customers get from this technology. Now, in terms of just how the system goes in, the architecture, it is a wireless system, and it connects to your old pneumatic system, right? So again, every place where you have an existing pneumatic thermostat, just take that one off. You screw the new one back on. The holes are already pre-drilled. You don't even have to drill new holes. There's a mounting plate to stick it on, and then you press the button and you connect it to the wireless system. The wireless system has repeaters on different floors, and then the signal comes back to this box in the middle called a green box controller. So one green box controller has can control up to 225 thermostats, and then the green box controller itself is usually then connected to your Ethernet, and then it would talk to an existing automation system. So if you have a ALC or a Honeywell or Johnson or Siemens, it'll talk BACnet over IP, which is an open protocol. It works with all these different vendors. You can just do an auto discovery. All these new thermostats will show up as digital thermostats, and you can just drag and drop them and configure them just like BACnet thermostats. But the only difference is it's a fraction of the cost, and it's really easy to put in. So this whole bottom part of the slide here, that's the new technology that we're talking about. It's the wireless system, the new wireless pneumatic thermostat, the green box. And once you put that in, it talks with whatever system you have there already. Now, if you don't have any system there, then we also have a built-in head end. So it's sort of a poor man's head end that you can still get. You can change set points, you can trend, you can get historical data, you can get text messages. So, you know, some buildings have nothing at all. So if you put this one in, you at least get the minimum. You get this head end where you can get the functionality of the trending, the alarming, the set point control. Okay. And I have some pictures here how it integrates with other systems. Yeah, obviously we've won a lot of awards for doing this, but I think mainly what I want to share with you is really we've learned a lot from the customers that we've worked with so far. So I talked a lot about the pneumatic thermostat. I think I'm probably out of time, right? So I'll take some questions, or if there's interest in the other areas, please stop by.